The overall goal of this procedure is to provide a method to obtain a three-dimensional structure of helically assembled molecules using cryo-electron microscopy. The protocol begins with cryo-EM specimen preparation, using a rapid dilution and backside blotting method to transiently reduce the salt concentration when preparing the frozen hydrated EM grid. This process ensures protein stability while reducing background noise and improving the signal-to-noise ratio during the cryo-EM low-dose data collection that follows. Subsequent to data collection, helical indexing of diffraction patterns is completed. Image processing is then performed, followed by real-space 3D reconstruction, resulting in the final density map of the HIV-1 capsid, or CA, tube.
Generally, individuals new to this method will struggle because there are several critical points for optimal data collection and analysis. For example, in the case of HIV-1 capsid tubular assemblies that only form in 1 molar salt solution, rapidly reducing salt concentration without affecting the structure is critical to obtain high-quality cryo-EM images. Given a tube image, it is very difficult to learn what to do to index a helical tube and which software could be considered to do 3D reconstruction. This video provides a detailed and straightforward approach to obtain a 3D reconstruction of helical objects and could be used as a reference for your experiment. I will be demonstrating the procedure with Dr. Gongpu Zhao. We are both postdocs from Dr. Peijing Zhang's laboratory.
To prepare the HIV-1 capsid protein assemblies for cryo-EM, begin by glow discharging the carbon side of 200 mesh copper grids under 25 mA for 25 seconds. Use a nebulizer to bring the humidity to 80% in the environmental chamber, which is a homemade manual gravity plunger. Meanwhile, cool liquid ethane in a Vitrobot plunger dewar with liquid nitrogen. Mount the plunge freezing dewar onto the manual gravity plunger. Next, use forceps to clamp the pincers closed onto the grid edge. Apply 2.5 microliters of a pre-assembled protein solution onto the carbon side of the grid. Then load the forceps onto the plunger with the carbon side of the grid facing away. Add 3 microliters of low salt dilution buffer to the back side of the grid. Immediately blot the grid with a piece of filter paper on the same side. Keep the whole back surface of the grid in close contact with the filter paper for approximately 6 seconds. After removing the filter paper, immediately plunge the grid into liquid ethane. Finally, remove the forceps from the plunger and quickly transfer the grid into a grid storage box. Begin cryo-electron microscopy by loading the frozen hydrated grid into an FEI Polara G2 electron microscope operating at 200 kV and equipped with a Gatton 4K x 4K CCD camera. Under low-dose search mode, at a magnification of about 200x, screen the whole grid for areas with suitable ice. Save the positions of these areas in a stage file. Recall the saved positions and further screen these areas at a magnification of 3900x in low-dose search mode. Select the areas with uniform thin layer ice for data collection, which are characterized by containing long tubes suspended over a hole. Save all the areas in a second stage file. Switch to exposure mode at a magnification of 59,000x and inset a 100 micrometer objective aperture. Then adjust the objective stigmatism and beam intensity for a dose of approximately 15 electrons per angstrom squared per exposure. Return to the low-dose search mode and move to a saved position. Identify and center a good tube using the CCD camera. Switch to the focus mode, adjust the focus, and set a defocus value, normally between 0.5 and 2.5 micrometers. Then, switch to the exposure mode and set an exposure time of 0.3 to 0.5 seconds for a dose of 15 electrons per angstrom squared. Collect the images on a plate camera, allowing the films to settle for 10 seconds before an exposure is taken. Following collection of images, Move to the next saved position and repeat this process to collect more images. Develop the films in full-strength D19 for 12 minutes. Then digitize the images using a Nikon Super CoolScan 9000 ED scanner at a pixel size of 6.35 micrometers. A helical object can be indexed by two parameters: the Bessel order, n, and layer line number, L. In the Fourier transform of a helical object's surface lattice, each layer line is characterized by n and L, and corresponds to a set of lines on the surface lattice as denoted by h and k indices. To begin helical indexing, use the Iman's program Helix Boxer to box out a relatively long and straight tube with uniform diameter and save the image in MRC format. Then measure the radius of the tube using Iman's program Boxer. Determine the helical repeat distance using a cross-correlation-based program, such as IMG-CCF in the MRC package. Then calculate the Fourier transform with a new box length that is an integral of the repeat distance. Next, choose two principal layer lines that define two basic surface lattice vectors, 1, 0 and 0, 1. In units of FFT pixel, determine the layer line numbers as well as the radii of maximum amplitude for the two principal layer lines in the Fourier transform. Given the layer line numbers and the values of Bessel orders for the two principal layer lines, the rotation between subunits and the axial rise of the one-star helix can be obtained using the selection rule as described in the written procedure. These two real numbers describe the screw symmetry of the tube. "3D reconstruction begins with particle segmentation using the Iman program Boxer. After opening a micrograph containing helical particles, cut a particle into overlapping segments. In the control panel of Boxer, choose helix mode and set the parameters for boxing. The size of the box should be larger than the diameter of the particle, and the value for OLAP should be about 90% of the box size. After left-clicking on either end of the particle, Boxer will automatically generate a series of particle boxes along the helix length. Save the boxed segments as well as their coordinates. The next step is to perform initial 3D reconstruction using the iterative helical real space reconstruction method, IHRSR. Prior to processing with IHRSR, invert the contrast of the cryo-EM images and apply low-pass filtering. Then open the graphical interface of the IHRSR program by typing generator. Provide the graphical interface with all the information for the boxed particles stack, including the name and path of the stack, number of images in the stack, and the values for symmetry parameters. Click the Finish button to create the reconstruction script, b25.spi. Use a solid or hollow cylinder as an initial reference, and allow the procedure to cycle until there are no changes in the defined screw symmetry, which usually occurs after a few cycles. A right helical symmetry should give a stably converged reconstruction. The reconstruction generated in the last cycle will be used as an initial reference for further refinement. Finally, perform 3D reconstruction with iterative refinement using the 3D density map generated by IHRSR as an initial reference for additional refinement. During the refinement, the helical symmetry is fixed at the rotation between subunits and axial rise, which are determined from the IHRSR procedure. Next, determine the defocus and astigmatism present in the micrograph using programs CTF Find 3 and CTF Tilt. Using spider programs termed FT and mu, multiply particle segments by the contrast transfer function, abbreviated CTF. Perform projection matching by comparing projections of the reference volumes with the CTF-corrected images using multi-reference alignment. The variation in the out-of-plane tilt angle is limited to plus or minus 10 degrees and sampled in 1 degree steps. Introduce constraints such as high correlation coefficients, in-plane angles near 0 degrees or 180 degrees, and limited X shifts for the alignment parameters of each segment. Include in the reconstruction only those segments that satisfy the constraints. After each iterative refinement cycle, a 3D reconstruction is generated using back projection and divided by sum over the CTF squared. Impose the helical symmetry to generate a symmetrized volume. The iterative refinement is terminated when no further improvement in the resolution of the new 3D reconstruction occurs. A single HIV-1 capsid assembly A92E tube was boxed out and its Fourier transform was calculated for helical indexing. The tube radius, the layer line numbers, and the radii of maximum amplitude for layer lines 10 and 01 were determined. N values of -12 and 11 were then calculated for 10 and 01 respectively. With a repeat distance of 5,195.48 angstroms, the screw symmetry of the tube was determined as delta Z equals 6.81 angstroms and delta phi equals 328.88 degrees. Delta Z and delta phi were refined to 7.13 angstroms and 328.86 degrees using IHRSR, and an initial reconstruction was generated after 10 iterative cycles. The final reconstruction, after iterative refinement, improved the density map significantly from the initial model calculated with IHRSR. The density map of capsid assembly tubes is displayed as 3 orthogonal slices, parallel to the tube axis and close to the surface, perpendicular to the tube axis, and parallel to and through the tube axis. The displayed structure results from surface rendering of the 3D density map contoured at 1.8 sigma enclosing 100% volume.
After watching this video, you should have a very good understanding of how to obtain a 3D structure of helically assembled molecule using cryo-electron microscopy.